Welcome back, friends. So we were discussing about representations of unitary groups or orthogonal groups yesterday, essentially, in the last lecture, and today we'll continue to do that, and we'll see the connection with the Lorentz group, and then how do everything falls in place, essentially. So we were started with the O3. Okay. Now O3. We say that it's a non-abelian compact group, essentially, which is represented by three angles, theta, psi and phi, and along the way we started going for it's a compact group because in the sense that its domain is sort of fixed, essentially. One of the main things that it forms a Lie group is that it can be expanded around unity in terms of infinitesimal transformations. So you can express this in terms of exponential of this angles. So these are your generators, and these generators are typically Hermitian. They are all Hermitian. Okay. In this case, that they are symmetric. That's all it means, essentially. Orthogonal, essentially. Yeah. Antisymmetric in real sense, essentially, in this case, in the case. So now we'll see the case of unitary groups in a second. Now, and these generators satisfy this algebra, which we call as the Lie algebra. Then we ask the question that, okay, now what happens if we have non-compact Lie groups, and this is where the discussion was going on, essentially. So we ask the question that if I replace cos theta by cos xi, what will happen? Okay. So this is exactly like in Lorentz boost, essentially, that you can have a situation in this particular. You can write a Lorentz boost generally in terms of cos hyperbolic xi, sine hyperbolic xi. Okay, I didn't define what was cos xi. So cos xi is nothing but 1 by root of 1 minus v square. V square by c square, that is with c is equal to 1, this just becomes 1 by root of 1 minus beta. Beta is equal to v by c. Okay, beta square. And whereas sine xi, I'll write it again, essentially, is beta gamma, essentially root of 1 minus v square by c square. So this is nothing but v, okay, v by root of 1 minus v square by c square. Okay. So this is the definitions of sine xi, and this is exactly like a boost, essentially. Now the point is that a boost don't, I think yesterday I said that they can form a group or something, I mentioned, essentially. Well, they one can have boosts, essentially. These boosts are essentially, they conserve this line of movement. Even you can think in terms of rotation, but technically they don't really form a group. Now this is not completely correct because they don't close into each other, essentially. They don't close into okay. Now we represent it like a group, but boosts don't himself really form a group. Boosts do not form a group because sometimes what happens is two boosts okay, I think there is some what happens is two boosts, they need rotations also to form a group. I think last time I mentioned that they themselves form a group. I think that was the mistake. It was propagated in while teaching because I wanted to introduce this boost as a concept. Okay, but typically boost on their own, okay, maybe that was a on their own do not form a group. If you take a group made up of pure boost only, you want to construct a because they don't close to each other, meaning if you put one boost after another boost, you need a rotation to come go to that place, essentially. You want to go to that scenario, essentially. So boosts themselves do not form a group, and of course they do not commute. One can have boost in 3 directions, and the generic boost can be written to similar to, you can write the language of rotations and everything, but they don't actually form a group. But so now coming to today's lecture essentially, but boosts plus rotations form a group, and this is nothing but Lorentz group. So this is the group which is called the Lorentz group essentially, which is the group of Lorentz transformations, group of Lorentz transformations. Okay, so when I mentioned last time about the boost, essentially there was a slight point that I didn't mention together with the rotations. I mentioned as though that it might have appeared that boost on their own form a group, but what I meant was essentially that boost along with rotations form a group essentially, along with rotations. That's the important point essentially. Along with rotations form a group, and it's a non-compact group essentially. So it's good idea that how Lorentz transformations form a group, and we can start with Lorentz transformations and then derive the group algebra from that. Now before doing that, there is one more ingredient which we need, which is called unitary groups. Okay, I'll introduce unitary groups and their representations, and then we will go to Lorentz group and why it forms a group along with. So there are rotations, there are boost, and together they form a group. Rotations alone form a subgroup of Lorentz transformations, but boost do not form a subgroup of Lorentz transformations, and we will see all this details essentially. Now before doing that, I also want to introduce one more concept in group theory which is extremely important, which is called unitary groups. What are unitary groups? Unitary groups are groups made up of unitary matrices which are defined by U dagger U is equal to 1. So these are in complex vector spaces essentially. These are complex matrices, and complex matrices with the definition that U dagger U is equivalent to 1. So now in the case of orthogonal groups, our vectors are essentially real vectors. So our vector spaces are real vectors x, y, z, so on so. And the rotation group is a group of transformations acting on the real vector space essentially, acting on the real vector space. Okay, so just to in the case of orthogonal groups, the rotation group consists of transformations which are nothing but rotations on vectors, vectors which are real vectors, which belong to real vector space Rn, say for example, which are all real vector spaces essentially. Okay. So, what we are looking at, so we will come back to this definition because I will mention the word such a thing where you have a vector space which is real. So, it is called a representation. So, you have in the form of the matrix which is a transformation which is given in that particular vector space is called a representation. So, both the vector space as well as the transformation given in a matrix form represented in that vector space is called a representation. Okay, that is called a representation. Say for example, O3 has the representation such that it is given in terms of orthogonal groups essentially. O3 has a representation which is also the defining representation, that it is given in terms of matrices which are orthogonal to each other in 3 dimensions essentially. So, this is now you can so for unitary groups and orthogonal groups we have something called a defining representation. That means that vector space itself we choose is the representation through which we define the group itself. In general we can define rotations as some abstract operator acting on a vector space. Okay, some rotation as some abstract operator acting on some vector space. But if you specifically mention what is a vector space is and specifically mention the representation of the rotation, essentially what is how the matrix of the representation is, how the matrix is represented, that transformation is represented in that particular vector space is, such a thing is called a representation of the abstract operator essentially. Okay. So, any transformation can be some abstract operator defined on some vector space. Now, if you specify what that vector space is and if you specify what that matrix is in particular to that vector space, that is called a representation. Okay, that is called a vector representation. Okay, let me just write it down essentially that if one specifies any transformation can be defined abstractly as an operator acting on a state vector, okay, using quantum mechanical language, or an vector space essentially, vector space. But once we specify the vector space, it could be real, complex, how many dimensions, etc. all the attributes which are required to specify the vector space and represent the transformation also as an matrix in the specific vector space, such a vector space as well as the matrix are called representations. So, in other words, essentially now you can choose. So, for example, if you take O2 and I take a representation, okay, what I call it as a defining representation is defining representation is vector space of dimension 2. So that would be x and y. Okay. So in x and y space, I can define O2 in terms of a matrix, okay, in terms of cos theta, sin theta, minus sin theta, cos theta. So this is a representation of O2, and such a representation is called fundamental representation. So why it's called fundamental representation is that the dimension of the vector space and the dimension of the group are the same essentially. So the dimension of the vector space and the dimension of the group are the same. O2 is a group of rotations in 2 dimensions. Now you can say what is so great about fundamental representation. So what is the so great? So it's a defining representation also. It's also in the case of O2, it's also the defining representation, because you define the O2 group in terms that it is a group of rotations in 2 dimensions. So it is like a defining representation also. So the way this is also a defining representation. You are defining the group in terms of a representation, okay, in terms of a defining representation. Now you have to, why this is because representations, the group can be defined without a representation also. Say for example, you can take a abstract group of 4 elements, apply all the group axioms and everything without any representation with an abstract group essentially, and then work it out. But for continuous groups, it helps to define it in terms of a representation essentially. Now that is the reason why we distinguish between abstract discrete groups and also continuous groups essentially. So in continuous groups we try to define. Now what happens for 3 dimensions? So 3 dimensions also you have the same 2-dimensional rotations can also have 3-dimensional representations. Say for example, you consider a vector space dimension 2. So you have x, y, z. Okay. So here you can have rotations in yz, xy plane, which is only 2-dimensional, yz plane or something like that. Okay. So this, the generators of this are nothing but your, so for example, the generators in this case are nothing but 1, -1, 0 essentially. So here for dimension 3 of O2, the generators would be something like this essentially. You will have 0, 1, -1, 0, 0, 0, 1, 0, 0. It's a 3-dimensional representation, but it is still a representation of the O2 because it only gives you rotations in 2 dimensions. It only gives you rotations in 2 dimensions. Okay, it may be a 3-dimensional vector, but it only represents rotations in 2 dimensions. Okay, the generators, this is not a fundamental representations of O2 dim3. You can also shift this thing to bottom and put 1 on the top, so that is also possible, or the other way around essentially. So but this is only O2 representations of dimension 3 essentially. Okay. Now these are not O3 generators. You see that these are not O3 generators, but O3 generators are different. So if you remember your O3 generators are, okay, we have done it in the class essentially. So these are your O3 generators essentially. So these are your O3 generators. Now that we had defined something for representations and so on, so that you have to remember that there is a vector space essentially. There is a vector space in which you use to define. You can have various vector spaces essentially, all kinds of vector spaces, but the group action should be the same. It should represent the same thing. It should represent, say, rotations to 2 dimensions should represent only the rotation is 2 dimensions, even for an n dimensional vector space essentially. That is a task of a representation. So there is only one group essentially. Okay. Now let's do one more thing. Okay. So what happens if the vector spaces are complex vector spaces? Suppose instead of having real vector space x, y, z and everything, so instead of having that, you have vector spaces like z1, z2, z3, whereas where zi belong to C, complex numbers essentially. So if you have complex vector spaces, so you need complex matrices which are multiplying this. So this will be A, B, C, F, G, H, I, where A, I belong to, say, again complex numbers essentially, complex numbers. Okay. Now what happens? How many number of parameters you can have for rotations with complex vector spaces essentially? We'll ask the same question. What are the generators in this case, and what happens to the rotations in this particular case essentially? So to make our life simpler, let's just say for example that I start with 2 dimensions. Let us start with dim2. Let's start with dimension 2, and now we have a vector rotations in 2 dimensions A, B, C, D acting on z1, z2. So complex vector of 2 dimensions. So this matrix is acting on this essentially. Now we ask the question that what are the conditions? Okay, what are the conditions? So this will go to, so z1, z2 prime. Now in the case of rotations, we said x square plus y square, which is the norm, which is the length of the vector, to be the same essentially. Now we will ask the same question that what are the conditions under which, what are the conditions on this R? Now instead of R we will use the letter U. Okay, such that z dagger z, if you call this as z, z dagger z is equal to z dagger prime z. So that means z dagger z will be invariant. What is z dagger z? What is z dagger z? Z is this vector. So z dagger is equal to z1 star, z2 star, and z. Okay, this is z again. Okay, z1, z2. So z dagger z is equal to z1 square plus z2 square. Okay, so this is exactly like the norm of the vector, but it is now called it's essentially exactly like the length of the vector, but this is the norm of the vector. So the norm of the complex vector is invariant under a transformation. Okay, let's call it as a rotation essentially, which is like a rotation in complex space. So let's say this call is this operator U. So this means that z prime, okay, z prime is equal to U times z. So z prime dagger is equal to z dagger U dagger. So what we have is z prime dagger z prime is equal to z dagger u times z, and that should be equivalent to z prime dagger z dagger z. Okay. So this is the condition we have. So this means u dagger u is equal to 1. So this transformation u should be unitary. So unitary is essentially what we defined. Okay, u dagger u is equal to 1. So this is the condition we end up with essentially. So these are unitary matrices. Similar to orthogonal matrices, but with the condition, because these are complex, you have u dagger u is equal to 1. Now let's take a generic u in 2 dimensions. We have written it u b c d. You have u dagger is equal to a star b star c star d star. What I did was essentially take the complex conjugate and transpose of it, essentially take the complex dagger is complex conjugate and transpose is equal to, now this I can multiply these two. So I have a square plus b square. Now a c star plus b d star, then this is a star c plus b star d, and this is mod b square mod c square plus mod d square. Let me write it neatly. This entire thing, the condition should be that it should be equivalent to 1. So that is 1 0 0 1. So what we are doing is exactly like what we did with orthogonal matrices. We are trying to calculate how many independent parameters are required to explain a unitary matrix essentially. So let's see the conditions. Now first of all, let's count the number of parameters. There are 4 complex parameters. So a b c d are 4 complex parameters, that is equal to 8 real parameters, 1 for the imaginary, 1 for the real part essentially. And then there are these 4 conditions 1 2 3 4, and all the 4 are independent, because one is a c star plus b d star and a star c plus b d star. So that means you have 4 conditions. So that is 4 parameters are required. So what we have in general U matrix, unitary matrix essentially, for a general unitary matrix has general unitary matrix is defined by of dimension, for a dimension n, number of parameters is equal to 2n square. Okay, number of parameters is equal to 2n square, because they are complex. N square is the number of complex parameters. So 2, because there is a real and imaginary part essentially, so there is 2n square. And number of conditions is equal to n square, n into n. So n conditions essentially n square. So the number of parameters for n dimensional unitary matrix is equal to 2n square minus n square, that is equal to n square. Okay, with n square parameters essentially you should be able to get all the specify a unitary matrix. Now we will put one more condition which is called special unitary. The special unitary matrix is defined by det of u is equal to plus 1. As we have seen, if you have u dagger u is equal to 1, det of u square should be equivalent to 1. So det u can be both the choices plus 1 or minus 1, but if I choose a plus 1 condition, it becomes something called a special unitary matrix defined by SUN. So if you have UN has n square parameters, SUN, because of this extra condition, SUN will have n square minus 1 number of parameters, essentially n square minus 1 number of parameters. So so you have so one parameter less compared to the general unitary matrices, essentially. Okay. So now what is this all to do about? Spinors are vector fundamental representations, can be thought of also as fundamental representations of SUN matrices, essentially. Sometime, okay. This is not of SUN matrices. So this is the basic idea, essentially. Okay. So that is why we came all this way to do group theory, essentially. So we to do group theory. Now how that, okay, so this is sort of tells you why we introduced orthogonal groups, rotation groups, and then connect compact, non-compact, and so on. So, and now finally we have ended up with having unitary groups, and these unitary groups we could redo what we did with orthogonal groups, so we could move very fast, essentially. So essentially unitary groups are like exactly the same thing like what we did for orthogonal groups, but for complex vector spaces, essentially. With this we have defined the number of parameters, and so what we are saying is the unitary or fundamental representations of unitary groups, all the transformations of unitary groups, essentially, or of matrices, or matrices are representations of groups, essentially. So spinors are fundamental representations or the vector spaces associated with SUN transformation matrices, essentially. Okay. So we'll stop here. Okay, we'll stop here and then we'll come back and take it forward from here on in the next class, essentially. So now you have some idea about group theory, what are orthogonal groups, what are compact and non-compact groups, and what are unitary groups. Now we will try to understand what is the Lorentz group, and then from the Lorentz group what are the connections to the Dirac equation and the representations of the Dirac, of the Lorentz group, essentially. So I'll stop here. Thank you very much. Thank you.